Alright guys, today what I'd like to do is go through some of the homework problems that you've had recently and make sure that everyone's on the same page and we all can figure out how to solve these problems. So basically what we've been looking at is equilibrium problems, so problems where the forces all cancel out to zero and we can exploit that fact to help us solve for unknowns. The first homework problem that I'd like to look at is problem 52. In this problem, you had a situation that was very similar to a problem that we went over in class, except in this case you have a helicopter, which I've just drawn amazingly poorly. So there's our helicopter, and it's not getting any better. So the helicopter is actually flying straight forward with a constant velocity, and we're told that it has a weight downward. There's a force of air resistance, which is capital R. Um, and the lift of a helicopter, the way a helicopter flies is actually by tilting the main blades and the whole helicopter, in fact, forward, so that a component of the lift moves the plane forward and the other component of the lift keeps the plane in the air. In this case, the lift is pointed at some angle and we want to figure out the value of the lift. Okay, so in this situation, the lift vector is actually pointed at some angle away from vertical, some angle theta, and the weight is directly downward, and air resistance is directly backward. Unlike the problem we did in class, in this case we really don't need to rotate the coordinate system because we can actually just split the lift vector up into the x and y components. Okay, so that's probably what we're going to do here. Let's look at the y direction. So if it's traveling in equilibrium and there's no acceleration, then the net forces in the y direction should cancel out. And the only forces acting in the y direction are the y component of the lift and the weight, which is downward. So I'm going to say minus, and that has to equal 0 newtons. So the y component has to be equal to, but opposite in direction to, the weight. The y component of the lift, if I look here, is actually equal to the cosine of theta. If I look at this triangle here, I'll see that L sub y is the adjacent edge for that angle, so that would be cosine. So that's going to be L cosine theta is equal to the weight, or the lift is equal to the weight divided by cosine theta. I can do the same thing for the air resistance. In this case, I'm going to use the x direction. And again, the forces should cancel out so that I've got 0. The forces in the x direction are the x component of the lift that's moving the plane, or at least got the plane moving forward in the first place. And this, at this point in time, it's resisting air resistance, or fighting against air resistance, and those should balance out to be 0. Again, we'll see that the magnitude of the x component of the lift is equal to the air resistance, or air resistance is equal to L times the sine of theta, and so that is our answer. you can plug in the values that they gave you, which were that the weight was equal to 53,800 newtons and the theta was equal to 21 degrees. Use those two values, you can find the lift and the air resistance. The next problem that I want to go over is problem 53. In problem 53, they tell you that you have some random object and you're exerting a force, I'm going to call force 1, that's equal to 80 newtons, and you're doing that directly north. And you're exerting some other force directly west, I'll call that force 2, at 60 newtons. And they want to know the direction and magnitude of a third force that would balance all of this out and make it so that the object doesn't have any acceleration. So the trick here is to realize that force 3, its components, the component in the y direction and the component in the x direction, need to exactly cancel out force 1 and force 2. Let's do the y component first. So this needs to be 0 newtons. So force 1 is in the y direction, plus the y component of force 3, and those need to cancel each other out. So force 1 is going to be equal but opposite in direction to the y component of force 3. So that tells me that force 3's y component is actually equal to negative 80 newtons. I can find the x component in the same way by saying that the x component of force 3 plus the force 2 has to be equal to 0. So that's x component of force 3 equals negative F2. Force 2 is 60, but it's pointed to the left, so that's already negative. So force 3 is going to be 60 newtons. Those are my two forces. I can solve this now by saying that force 3 is equal to the square root of the sum of the squares. And I can find the direction of the angle by using the inverse tangent. Okay. If you plug in the values given to those, you'll find the magnitude and direction for that vector. Alright, the last problem that I want to deal with is 59. For problem 59, you're given a wine bottle that's sitting in a rack, and they tell you a couple of bits of information about that. They tell you that this rack was built so that the two pieces of wood meet at a 90-degree angle, and they also tell you that the wine bottle rests exactly in the middle, so that that angle is bisected. That tells us that these two angles here are actually 45 degrees. And the forces that are exerted on the wine bottle are actually going to be perpendicular to these surfaces. The normal force is what's keeping it in place, so I've got one force there and one force here. If I draw the free body diagram for this, here's the wine bottle. Here's one of the forces acting up in that direction and the other force acting in this direction. What I need to do is figure out what is the angle of these forces from the horizontal. In fact, if we look over here, this vector is parallel to the plank of wood that forms the rack. Same thing over here. So the angle is actually going to be, again, 45 degrees. We can see that the x component of these two forces are going to cancel out. They're going to be equal in magnitude, but opposite in direction, so they'll cancel out. And the y components of these forces will add together. What we can do is look in the x direction, so the net force in the x direction has to be equal to mass times acceleration in the x direction. If the wine bottle is just sitting there, it's got zero acceleration, so the net force in the x direction is equal to 0 newtons. The forces in the x direction are force 1 sub x plus force 2 sub x is equal to 0 newtons. Means they need to be opposite in direction but equal in magnitude. In this case, the x components are going to be cosine, so that's going to be force 1 cosine 45 degrees is equal to negative force 2 cosine 45 degrees. I can divide 45 degrees from both sides and I'll get, like we thought earlier, force 1 is equal but opposite in direction to force 2. I can use this fact to help me out in the next dimension. So the net force in the y dimension has to be equal to mass times acceleration. Again, this should probably be 0 if we want the wine bottle to survive any length of time. So I've got F1y plus F2y minus the force of gravity is equal to 0 newtons. So these are the two y components of the forces caused by the case and the weight of the bottle. These need to cancel out, so the bottle has no acceleration and it sits there at rest. We just said that force 1 and force 2 are equal to each other, so I can just say 2 times the force in the y direction minus the force of gravity is equal to 0 newtons. And then the y direction is just F sine 45, so this is 2 times the force supplied times the sine of 45 degrees equals the weight. And so we can use this to solve for the force supplied by the case. It's just going to be equal to the weight of the wine bottle divided by 2 sine 45 degrees. We plug in the values that they gave us in the problem. That'll lead us to the answer.